to quantum-safe cryptography. With the rise of quantum computing, traditional cryptographic algorithms such as RSA and ECC are at risk of being broken due to Shor's algorithm, which can efficiently factor large numbers and compute discrete logarithms. To mitigate this risk, post-quantum cryptography (PQC) focuses on developing cryptographic schemes resistant to quantum attacks. This lecture explores quantum-safe cryptography, its importance, and practical implementations using modern programming techniques. We will cover lattice-based cryptography, hash-based cryptography, and code-based cryptography, with hands-on code examples. Understanding quantum threats. Classical versus quantum computing. Classical computers rely on bits, zeros and ones, to perform computations sequentially or in parallel. Quantum computers use qubits, which exist in superpositions, enabling exponential speedups for certain algorithms, e.g., Shor's and Grover's algorithms. Key quantum algorithms. 1. Shor's algorithm efficiently factors large numbers, breaking RSA and ECC encryption. 2. Grover's algorithm speeds up brute force attacks, reducing AES 256 security to AES 128 levels. Post-quantum cryptographic algorithms. To defend against these threats, researchers are working on quantum-safe cryptographic algorithms. Some major categories include 1. Lattice-based cryptography. Based on hard problems like learning with errors, LWE, and ring LWE. Examples: Kyber, key encapsulation mechanism, dilithium, digital signature scheme. Example: lattice-based encryption using Kyber. Explanation: a key pair is generated. A message is encrypted using the public key. The message is decrypted using the private key. The shared secret remains consistent between encryption and decryption. 2. Hash-based cryptography. Relies on hash functions for digital signatures. Example: Sphinx Plus, stateless hash-based signature scheme. Example: hash-based digital signatures, Sphinx Plus. Explanation: the message is signed using a private key. The signature is verified using the public key. 3. Code-based cryptography. Based on error-correcting codes. Example: Michaelis cryptosystem. Example: code-based cryptography with Michaelis. Explanation: Michaelis is used for public key encryption. Key pair is generated, a message is encrypted and decrypted securely. Implementing quantum-safe solutions in practice. Migration strategies. 1. Hybrid cryptographic approaches. Use both classical and post-quantum algorithms for encryption. Ensures security against both classical and quantum attacks. 2. Updating cryptographic protocols. Transition to NIST recommended PQC algorithms. Ensure backward compatibility and phased deployment. 3. Integrating PQC into existing systems. Software-based PQC implementations allow for easier adoption. Hardware acceleration for efficiency. Challenges in adopting PQC. Performance overhead. Post-quantum algorithms can be slower. Key sizes. Larger keys may require increased storage. standardization and compatibility, ensuring secure and seamless adoption. Conclusion: quantum computing presents significant threats to current cryptographic systems. Transitioning to quantum-safe cryptography is essential. Lattice-based, hash-based, and code-based cryptographic algorithms offer promising solutions. Organizations should start adopting hybrid cryptographic methods and preparing for a post-quantum world today.